Hello, so today we're going to be talking about atomic absorption spectroscopy. And if you watch the introduction to spectroscopy video, you'll know that spectroscopy is looking at the way that different atoms and molecules interact with light. This means that we're going to refine the idea of flame tests that we've looked at in the past and see how that can be used analytically. This machine here is actually an atomic absorption spectrometer. And what you can see here is there is a large flame in here. This is where our sample goes in. So you can see that it is in a solution form. So we have our sample here. There's actually a lamp in this bit here and a detector. But it's important to notice this flame that is in here because this is where our sample will pass through. We'll get the excitation that we're talking about. So let's have a look at it. So AAS, as it's known for short, stands for Atomic Absorption Spectroscopy. Okay, so flame tests tend to look at the color of emitted light. In this, we're talking about absorption. So we're talking about when the electrons are jumping up to that higher level and they're absorbing the energy. So we're looking at the energy that's missing rather than the energy that's being re-emitted out. This light is, as we've mentioned before, of specific wavelengths because of the unique electronic structure of each atom. And it's always a vaporized sample. So we have a solution that is passed through a very fine tube and turned into a mist, much like what happens anytime you press the button on an aerosol and you get that mist of propelled liquid that's very easily turned into a gas. That's the kind of thing that we're talking about. This absorbed light, so as it turns into a gas and comes into contact with the flame, it absorbs light of the specific wavelengths because of the electron jumps. It's an invention that was actually designed in Australia by CSIRO, which is one of the amazing things that CSIRO has contributed to the wider scientific community. Australia certainly bats well above average in terms of discoveries and contributions to science. We have a really great history in terms of scientific discoveries, particularly the scientists at CSIRO. So it's a very versatile technique. It can detect 68 elements. Okay, so it's able to detect the presence. It's very sensitive and it's able to detect the presence of 68 elements. Remember, we said with flame tests, it can be limited dependent on whether or not they can be excited within a Bunsen flame. This is much hotter, so and the way that it works expands its ability to be used. And for us, when we're talking about water contamination and various things like that, it's important to note that this can detect concentrations as low as parts per million and parts per billion. So it's a fabulous technique if you think about for detecting low amounts of those toxic metals like heavy metals and things like that. Whereas where we looked at gravimetric analysis, you actually have to have a fair amount of the substance you're looking for in there to be able to form a precipitate. This would allow us to detect salts at a much lower concentration. So things like cadmium and things like that, which need to be present in, 0.003% or things like that, we're going to be able to detect those at much lower levels using this technique. So the solution, the sample is sprayed into the flame and vaporized. As I said, this goes up a tube, much like a aerosol can works. So then the light source of a specific wavelength is shone into the vaporized. So we're only having one selected wavelength. Okay, and this is important. It is shone onto a vaporized sample energy and is absorbed by electrons exciting energy levels. The light is then passed through a filter, so a monochromator, to separate the light of the chosen wavelength. So this filter helps to select the wavelengths that are used. And then the intensity of the light is measured by an electronic detector. So essentially, the light comes in, it passes through the sample, it's been selected, and then it measures the light that comes out the other side to see if we've lost any of that light. And of course, any light that is absorbed by this sample will be missing as it hits the detector out the other side. So the amount of light absorbed indicates the quantity of the element present in the sample because the light absorbed is proportional to concentration. Okay, so if we increase the concentration, then we would see more light being absorbed, and that allows us to work out exactly how much is there. So this is in a schematic form, and as you can see here, the lamp emits light required to excite the electrons. That beam of light is passed through the vapor in the flame, so there's enough energy to excite them here. The solution comes in through here into the flame, then it gets passed through. We select the wavelength we want to look at, and it is then detected over the other side to measure how much of it is missing. So the absorption of the light is directly proportional to the concentration of the atoms in the solution. We refer to this as the Beer-Lambert law. We don't learn the Beer-Lambert law in Unit 1-2, but that is the law that is operating here. So the amount of light absorbed by the sample is equal to the light emitted by the lamp, and then we minus the light unabsorbed by the sample, so the light that still comes through, the light that passes through. Okay, this means that the difference is the light that was absorbed, and that makes sense. And that light absorbed is proportional to the concentration. This technique is generally used in quantitative analysis, so it's not, remember that the flame tests were qualitative. We couldn't determine how much was there, just if we thought it was one particular element or another. This allows us to quantitatively analyze a solution and work out the specific concentration. This means we can work out concentration of these elements in blood, urine, soil, water, food. We can use it for drug detection. There's a myriad of things where this is used for low concentration. It can also be used qualitatively to detect the presence of the 68 elements it will work for. And importantly, these 68 elements are all metals. It only detects metal ions. Okay, and this is because it uses a lamp of the metal that we're looking for in order to produce the light. So what happens is that we use a cathode lamp of the element that we're looking for to produce that light of the specific wavelength, if that makes sense. So in this case, if we were looking for calcium, we would actually use a calcium lamp, has a calcium filament. That calcium lamp produces light that is made up of the specific wavelength required to excite calcium atoms and only calcium atoms. So we can use, if we want to find sodium, we'll use a sodium lamp. If we want to find magnesium, we'll use a magnesium lamp. So it only detects one element at a time. They're all metals, and we have to have the specific lamp to do the detection. The way we do this and the way we find a quantitative data from this is to use a calibration curve. This is the skill that really is critical moving forward from here, this idea of creating a calibration curve, because we create it for many different types of spectroscopy and for chromatography. So what this means is that we need to set up a series of samples that will give us a straight line of which we can interpret and interpolate from in order to get the value. So run with me on this. It'll sound a little bit confusing at first, but it will make sense. So we select the wavelength at which the component absorbs strongly and other components do not. So for AAS, we will have the lamp of the specific metal. So again, if I want to detect calcium, I'm going to have a calcium lamp. Then we will measure absorptions of standard solutions at this wavelength. So remember, standard solutions are solutions of known concentration. So this means I would take a pure sample of something that, a high quality of sample of something I wanted to analyze. So let's say we're doing calcium again. So we've got our calcium lamp. We would make up solutions of a known concentration of calcium ions. So we might start at 0.1 mole or 0.001 mole. We would make up a series of known concentrations, so maybe 10 milligrams per litre, because this can be quite sensitive, up to maybe 40 or 50 milligrams per litre. And then we would have different concentrations along the way, so 15, 20, 25, 30, 35. We would then take readings for each one of these samples in our machine, and we would get a reading for it. Okay, so that then means that we can plot a graph of these, run our unknown sample, and then interpret where it ends up on the graph. Okay, so this is the same process for all instruments that require a calibration curve. You make up a series of known standard solutions of varying concentrations from low to high, depending on what range that you want to, you suspect your sample will be in. You will run these on the machine, plot a calibration curve, and then you run your sample and interpolate from there where your sample ends up on the curve. So let's have a look at what this looks like. So this is our calibration curve. Okay, in this case, we've looked at nickel concentration. So a series of samples of the same element of known concentration are analysed and plotted on a graph. So you can see here that we have these would be the concentrations that were run. Okay, so 50, 40, 30, 20, and 10 milligrams per litre concentrations of nickel. And then the absorbance, this is the measurement from the AAS, from the Atomic Absorption spectrometer. It gives us a reading in absorbance, which has no units. And that is simply plotted onto the graph to give us this straight line. What this means is we could then take a sample of water that we suspected had nickel in it, and we would put it in, get its absorbance reading, and then say it had an absorbance reading of around 30. We would plot here, go across, and then we would be able to read down off the graph to determine the concentration of nickel in our sample. Okay, and that is pretty much what we do for all of them. So we're going to take the readings through the machine, plot a linear calibration curve, and then take the reading for our unknown and see what it turns out to be concentration-wise from the graph. So in all of these, we need to be able to plot a graph. So this is an example question of what it looks like. Atomic absorption spectroscopy is used to determine the lead concentration in soil collected from the side of the road. A student prepared a standard lead solutions for comparison, and the absorbance of each solution was measured. A roadside soil sample was also prepared. The results are shown in the table below. So what they've done is they have a sample. The blank is just the solvent minus any of the lead or anything else to give us a 0 absorbance reading from the machine. Then they've taken standard 1 with a 1 ppm concentration and recorded a 0.17 reading. Okay, standard 2, ignore the rest of the stuff on this at the moment. Standard 2 is 0.34, standard 3, 0.48, 4, 0.65, 5, 0.83. Then we can take that, we can plot it on the graph in order to work out the concentration. So if we plot the calibration curve using the concentration and absorbance of the standard solutions, okay, we will generate a linear curve. This is a line of best fit, okay, and only if you have a 0, 0 reading do you pass it through 0. Okay, if you're not given a 0, 0 reading, you do a line of best fit that doesn't pass through the origin. Then we're going to look at our sample reading. And if we look at the sample had an absorbance reading of 0.58. So we're going to go to 0.58 on our graph, draw a very straight, accurate line across to where it hits our line, and then drop that straight down to see that the concentration of lead in the sample was 3.5 ppm. So now we know accurately the concentration of lead that was in the sample of water. That's all it is. You do need to be able to plot the graph, so you will need a ruler, or you could use these on Excel since we're working online. But I want you to have a go, look at page 480, the worked example, give it a go yourself and try the key questions, and we will do some more examples in class.